All right, so we'll do kind of the steps of hypothesis testing. Okay. All right, so step one is write your hypotheses. Okay, and that's going to involve creating the null hypothesis and the alternative hypothesis, right? So you have your null and your alternative, and again, the null will always have an equal sign, and the alternative is identical to the null, except the equal sign has been changed to something else. Okay. Under step 2, the book calls this prepare. And so with prepare, what we often do is we check the conditions for the central limit theorem. Okay, so you should do that. Checking the conditions, that's going to include the random and independent condition. What else do we have? Large sample and big population. So we want to make sure that all of these conditions are met. Okay. We're also going to pick something called a significance level. Okay. Choose or identify the significance level okay, and the significance level is alpha. Okay, and we most often use alpha equal to 5%, but the significance level can be other values. All right. Step 3 is calculate your p-value. Okay, and so calculating the p-value is often involves kind of a few steps. So this is at least for, you're going to find the standard error. Okay. And then you're going to find your test statistic, which is equal to kind of your reality or the observed value minus the expected value divided by the standard error. Okay, so kind of reality versus expectation. And you're going to decide, is the difference big or small by dividing by the standard error, okay? And then you look up your test statistic in the reference table. To get the p-value. Okay, and then lastly, for step 4, make your conclusion. And that is, if the p-value is small, specifically if the p-value is less than alpha, you will reject the null hypothesis. And on the other hand, if the p-value is greater than alpha, do not reject the null hypothesis. Okay, and we write do not reject, and we do not write accept. Okay, so often we think of not rejecting as accepting something. Here it is just you are not rejecting. So not rejecting something is not the same thing as accepting it. Okay, so let's try out another example here. Okay, so we want to say okay, let's say I've got a big pot full of I don't know, M&M candies. Okay, and we want to know, is over 20% of the candies red? Okay. All right, so you we'll say we take a handful of, we'll say 100 random candies. Okay, and we get 23 red pieces. Okay, and the question is, does this provide evidence that over 20% of candies in the tub are red? Okay, what do you guys think? I got 23% red. Is that significantly larger than 20%? Enough to convince me that over 20% are red? Yeah, you guys are saying probably not. Okay, well, we'll go through the test and we'll see what happens, okay? So our null hypothesis is going to be about the proportion that's red, okay? So we're going to say P is going to be the proportion that is red in the population. So proportion of red candies in the population. Okay, so we have a null hypothesis and an alternative hypothesis. This is step one, is coming up with the hypotheses. So what is our null hypothesis going to be? We're saying P, P is equal to 0.2. The null hypothesis always has an equal sign, and we're going to ask, is it 20%? Or do we have evidence that it is more than 20%? Okay, so we've got P is equal to 0.2 versus P is greater than 0.2. This is our null hypothesis. Okay, so under step 2 we can do the prepare, but we'll check conditions and I didn't say how many candies are in the tub, but we'll say there's lots and lots of them, okay? So we'll say check conditions, and then I'm just going to fast forward through this because we've already kind of covered this in last week, right? So we'll just say conditions are met. Is that okay? No one's upset about that?
You mean the like large scale?
Yeah, large sample, big population, random sample conditions, okay? Those things. We'll say check conditions, and we'll say conditions are met. and then we'll use alpha, the significance level, to be 5%. Okay, so sometimes a problem will say use this specific alpha. If the problem doesn't say that, use 5%. Okay. All right. So then step 3 is to do our calculations, where we find our p-value. Okay. P-value calculations. All right. So first off, we'll figure out our standard error. The standard error is going to be p. The book uses p0 times 1 minus p0, and that's fine, divided by n. Okay, p0 just means the value that shows up in the null hypothesis. Okay, so p0 is the number that appears in the null hypothesis. Okay, so my standard error is going to be the square root of what? 0.2 times 1 minus 0.2, or 0.8, divided by 100. I think this ends up being 0.04, is that right? I'm going to do 0.2 times 0.8 divided by 100, and I take the square root of that, and I get 0.04. So my standard error is 0.04. Okay. All right, our test statistic is going to be the observed value minus the expected divided by the standard error. Okay. So here we are talking about p. What did we observe? What was the proportion that we observed? 0.23, right? So I'm going to put the observed value is going to be our p hat. What would we expect under this if the null hypothesis were true? We would expect 0.2. So I'm going to just put p0 divided by our standard error. So this is kind of the formula that appears. So what we observed was proportion of 23%. We were expecting a proportion of 20%, and we got a standard error of 0.04. Yeah, question?
You get the 0.05. You said it says use A equals.
Correct. Yeah, this is just kind of like a default value. 5% is the default value. If sometimes the problem will say use this specific significance level. So alpha is known as our significance level. Sometimes the problem will say what significance level to use. If it doesn't say that, assume it's 5%.
So by it being 0.04, what do you mean like that? That's the standard. So anything less than that, 0.05 is extreme?
No, 0.05. This is a significance level. This comes into play only at the end. Okay, so this is just the default alpha.
So we'll use it at some point, we're just not using it now.
Yeah, this comes in, is used in step 4. Okay, but you kind of identify what it is in step 2. All right. Okay, so what I get is my test statistic is 0.75. Is that okay? My test statistic is equal to 0.75. So far, so good? Okay. I'm going to flip to the next page. You don't have to. Okay. And okay, so this is kind of where we left off. The relevant pieces are, these are our hypotheses, and then we did the calculations and we got our test statistic equal to 0.75. All right, and so now we have to decide what is our p-value. Okay, so these are, this is how we decide, okay? If the alternative, This is still step 3 in getting the p-value, okay? So still step 3. So this is this part is going from your test statistic to the p-value, okay? And this applies just, this is for chapter 8, okay? In chapter 9, this part changes, okay? But, You have much to look forward to next week. Okay. So as far as chapter 8 goes, okay, going from your test statistic to the p-value, okay? If the null alternative has a greater than sign, the p-value is equal to the area to the right, of the test statistic. Okay. If the alternative has a less than, the p-value is the area to the left of the test statistic. Okay. And if the alternative has a not equal sign, then the p-value is 2 times the tail area. Okay, what is the tail area? The tail area is the part away from 0. So I'll just, so the tail area is to the right for positive values, and the tail area is to the left for negative values. Okay, so yeah, as far as tail area goes, if you have something over here, this is the tail. Or if you have a positive value, right, 0 is always in the middle. This side will be the tail. Okay, so how do we decide what our p-value is in this case? What does our alternative have? It has a greater than sign, so we will use the area to the right, okay? Area to the right of 0.75. What is that? So the p-value here is going to be area to the right of our test statistic of 0.75, area to the right of 0.75, and that is, well, 0.2266, is that right? Okay, I will take you at your word. Okay, is that good?
Is that from the standard normal sheet?
Yeah, that'll be coming from your normal table. Yeah, you look it up in your normal table, and then you find the area to the right of z equal to 0.75 is 0.2266. Okay, area to the right of z equal to 0.75. Is this okay with everybody? Yes.
The last one, tail value. So if you get the area, it would be 1 minus the area, and then you say you multiply that by 2.
Yeah, if the alternative had a not equal sign, we would take this and we would multiply it by 2. Yeah.
Okay.
Yeah.
Whatever the decided value.
Whatever that. So you don't multiply the test statistic by 2. You look up the test statistic, get your area, and then multiply it by 2.
This number is for negative 0.75.
No, this is the area to the right of positive 0.75. Table always gives you the area to the left. So you're going to look up the area to the right, or area to the, you look up 0.75 and you get something like 0.7734, okay? And you want the area to the right, so you do 1 minus 0.7734, okay? But 1 minus 0.7734 is the area to the right of 0.75 is the same as the area to the left of negative 0.75, so you can do it that way too. Okay, good?
Can we, can you label your examples, step 1, 2, 3, 4?
Yeah, everything here has been step 3. Yeah, step 3 is a big one. Okay, I mean, I could go back and label this like step 3A, step 3B, and step 3C if you want. Okay, so step 3A will be the standard error, step 3B is the test statistic, and step 3C will be look up the test statistic to get your p-value. Okay? Okay, so then what we will do, so step 1 is the hypotheses, okay? And then right here, this stuff just, I'm sorry, the checking conditions and using alpha here, this is step 2, okay? P-value calculations, the standard error, this is 3A. The test statistic will be step 3B. Everyone so far so good? Okay, and then, sure. 3A is the standard error calculations, 3B is the test statistic calculations, and then going from your test statistic to a p-value, that's step 3C, okay? So the p-value, this is step 3C, okay? And these are the details for step 3C. Okay? Okay, so what we have right now is that our p-value is 0.2266. So far, so good? Yes? Okay. I'm going to continue on. Okay. So what we have is our p-value is equal to 0.2266. Okay? Do you remember what the definition of a p-value is? It's the probability of observing our data. Yeah, our data or something more extreme if the null hypothesis were true. Okay, so recall that our null hypothesis was that the proportion of red candies is 0.2. Okay, so the null hypothesis is that 20% of the candies in the tub are red, okay? Okay, if that were true, what's the probability that a random sample ends up being 23% red or more? That a random sample of candy ends up 23% or more red. Okay? And the answer is our p-value. It happens about 22.66% of the time. Okay? Just from random chance. So the fact that we got 23% red in our sample could be a result of just random chance. It happens about 1/5 of the time. Okay? Or it could be an indication that more than 20% of the candies are red in the tub. Okay? It doesn't prove one thing or another. It just says, well, the candies in the tub could be 20%, and I just happen to get lucky in getting a bunch of red candies. Okay? And so So what we say is our p-value is 22.66. P-value is 0.2266, okay? Our significance level was 5%. Alpha was 5%. So remember this from step 2? And you guys were asking what does that mean? Okay, so all we do is we say our p-value is greater than alpha. Okay, our p-value is greater than alpha. And so what this means is that the results we got may very well have been from random chance. The results we see could very well be a result of random chance. Okay? And so, and I have to do this double negative thing, but I'm going to say, I do not have evidence that the proportion is not, proportion of red is not 20%. Okay? I cannot say that I have evidence that the proportion is 20%, because that's not true. Okay? All I can say is I don't have evidence that it's not 20%. And I know people hate this double negative stuff sometimes, but all I can say is that I don't have evidence that it's not, okay, but it doesn't prove that it is, right? It's just like when you played only 10 games with a friend and you only won 30% of the games. It's not proof that he's cheating, but it's also not proof that he's playing fair. Okay, so we can't say, so we would have to say I don't have evidence that he's cheating, okay, but we can't say I don't have evidence that he's playing fair. Either we can't, or I mean, we can't say that we have evidence he's playing fair. Yeah.
What's the point of doing such a thing if you're not going to find that?
What's the point? Yeah, that makes science hard. Okay, science is hard. It's a lot of times all you can say is I don't have evidence for this thing. Okay. Yeah.
Step 4.
Yeah. This whole page has been step 4. Okay, this whole page is step 4. Is making a conclusion from your p-value. Okay. Yeah. A lot of times you can just say we don't have evidence that there's any connection between these two things, okay? You cannot prove that there is no connection because only until you know the full mechanisms and understanding of the inner workings of things, which for anything more complicated than, a simple physics experiment, you can't say we know for sure that this is what's going on. All you can say is, I don't have any evidence of this, right? So, does some drug cause a certain disease? We can do a bunch of studies and we can just say, we have no evidence that it causes the disease or it causes this problem, health problem. But until we understand the full workings of the human body and everything like that, we can't say for sure that this thing has no lasting consequences or effects, right? So, all sorts of, like, you can go on the internet and you'll find all sorts of, like, crazy conspiracy theories about stuff, right? Like, are cell phones going to cause brain cancer, right? Right now, all we can say is, so far, we found no link. Do we know for sure that cell phones has absolutely no impact on your body or things like that? Yeah, so far we found no link. We can't say for sure. Who knows, right? So that's how this works, okay? And yeah, that's it. Yeah. Sure. This is going from a test statistic to a p-value.
So you got the p-value how?
I looked up the test statistic in the Z table. Okay.
0.75?
Yeah, the test statistic is 0.75. Yeah, look up 0.75 in the Z table.
So the area in the Z table is the product, right? The thing that we.
It will lead you to your p-value. I don't know what you mean by product.
I forgot. I think the Z score is what we look up the columns.
Uh-huh.
And the area is what's the numbers inside. Right?
Correct.
Product,
Yeah.
right.
Yeah. Okay, is that all right?
How's it equal to, it says 7734.
Uh-huh.
So you subtract that once?
So this is the rules, okay? If the alternative has a greater than sign, which is what we have here, the area is to the right of the test statistic, okay? So that means what? You look it up and you subtract the area in the Z table from 1, right? So you subtract area from 1. Okay, and then over here, if the p-value is the area to the left, then you just take the area. Okay, and then for the not equal to 2, you have all of this extra stuff to do. All right, is that okay? We'll do another example, all right, and then we'll make our lives more complicated by covering the next section in chapter 8. So, yay! It's all good, all right. This is I realize this is a lot coming at you all at once, but we'll get through it. You'll practice. You'll have a quiz next week. We'll be good, fine. Okay. Yes. You are welcome. But this is a statistical inference. This is what we've been building up to this whole time. Okay. This is where we can start making conclusions based on limited data. All right. Okay. So I don't know. Someone claims, says that, I don't know, the military, there's something loud out there, is 16% women. We'll say the U.S. military. Okay? Someone says that the U.S. military is 16% women, okay? And then let's say we want to know if this is true. Okay, so we take a random sample. We'll say 200 people in the military, and we'll say we count. I don't know. 27 women. All right. I'm just making this up, okay? No, this is too few. This is, oh no, it's fine. Okay, all right, whatever. Okay, we count 27 women. All right, so we'll say, does this provide evidence that the proportion of women is something other than 16%? Okay, what do you guys think? Yes? No? All right, so I mean the question is could the military actually be 16% women, and could, just from random chance, we ended up with a sample of 27 women, which is basically 13.5% women? Could random chance produce this sample? Or is it an indication that the proportion is something other than 16%? This is the question, all right? So you're like, well, maybe, maybe not. Okay, well, we're going to do the math and we're going to get our answer, okay? All right, so our null hypothesis, so I guess if you want me to label the steps, okay? Step 1, create our hypotheses, okay? So our hypothesis, we are expecting the proportion to be what? We are expecting P to be 0.16. And then the alternative, what is the question? It's saying, does this provide evidence that the proportion is something other than 16%? So we're going to go with P is not equal to 16%. Because the question doesn't say, is this evidence that the proportion of women is more than 16% or less than 16%? It just says something other than 16%, okay? Is that okay for step 1? All right, step 2, we would check our conditions. And just for the sake of time, I'm going to just say your conditions are met, okay? But you guys know how to check conditions, right? Check conditions, and we will say they are met, okay? The military is more than 2,000 people. We have 27 people who are women, over 10 who are women, and over 10 who aren't, okay? And then we'll say use alpha equal to 0.05. Now we could pick a different value, but we'll just go with that, okay? So step 3 is to get our p-value. All right, so we'll start with 3a, which is going to be our standard error. Okay, so our standard error is going to be what? P0 times 1 minus P0 divided by n. So 0.16 times 1 minus 0.16 divided by 200, exactly. Okay, so I got 0.16 times 1 minus 0.16 divided by 200. I'm going to take the square root of this, and I get 0.02592. Okay. Standard error, okay. 3b, this is our test statistic. We do observed minus expected, right? Question in the back.
So, let's say for step 2, if the conditions aren't met, we just stop there.
Yeah, if the conditions aren't met, you're not supposed to continue on in the test, okay? Now, it makes for a very tricky, as far as exam writing goes, okay, or test quiz writing, it's very hard to write a trap question where it's like the conditions aren't met and now like you stop and I can't ask any more questions or something. So
Most likely they will all.
yeah, so as far as, so the way I've handled this situation with the test is all of these questions, the conditions are going to be met and you can continue on in the math, okay? But then I have a separate section, kind of like on this quiz, where I say, can you check these conditions? And then you say they're met or they're not met, okay? Because otherwise it's like, I feel like I'm writing like sneaky bear traps where it's like, I ask all of these questions like, what's the p-value? There's no p-value because the conditions weren't met. I got you. Like, it just doesn't make sense to write questions like that. So, or it feels disingenuous, I guess. So, okay. So anyway, that is a good question. So I tried to avoid that on here. Okay. So the test statistic, you know, the reality versus the expectation, or the observed minus the expected divided by the standard error. Okay. So what is the proportion that we observed?
0.135.
Yeah. So our p hat is 27 divided by 200, or 0.135, okay? And our P0 is what's written in the problem. So here we have 0.135 minus 0.16 divided by our standard error, 0.02592. Okay, so what do we get? We get 0.135 minus 0.16 divided by the answer. And I get negative 0.96. This is my test statistic. Is this okay? So my test statistic is negative 0.96. Okay? I'm going to flip the page. Is that all right? Just 1 second, okay? You can take pictures, but I also post these online, right? Like, okay, all right. Okay, we got this? Not yet. That's next step 3C, or getting our p-value. Okay? Good? Okay. So step 3C is going from the test statistic to the p-value, right? Okay, so what is the symbol that shows up in our alternative? HA has not equal sign, right? So what does this mean? Our p-value is 2 times our tail area. Okay, and right now our Z is, our test statistic is what? Test statistic is Z equal to negative 0.96, okay? So we go to our Z table. Okay, and then so that we find the area to the left. So if I go to negative 0.9 and 0.06, you said, what is the area here? 0.1685, okay? Which is on the left, which is what we want, okay? So this is my tail area if it's, when Z is negative 0.96, okay, my tail area is the area to the left here. So I got 0.1685. So my p-value is 2 times 0.1685. It's 2 times my tail area. What is it? 0.1685 times 2, 0.337. Great. Okay, so that's step 3C. This is my p-value is 0.337. So far, so good? Okay. I did 2 times 0.1685, and I got 0.337.
So you found 0.1685 as the area.
Yeah, that's the area to the left of negative 0.96. This is our Z table. Yeah. Yeah. So there's a section on the, I don't know, earlier in your notes where it says if the alternative has a not equal sign, you've got to do 2 times your tail area. Okay. All right. So as far as step 4 goes, we have our p-value equal to 0.337. Okay. And then what is my alpha? Alpha is 0.05. So our p-value is greater than alpha, and this means what? We do not reject the null hypothesis.
Is the alpha always going to be given to us?
Yeah, so if the alpha is not given, assume it's 5%. Otherwise, maybe somewhere in the problem it will say, use a significance level of 1% or a significance level of 10%. Alpha is the significance level. If it's not specified in the problem, assume that it's 5%, okay? So it's like, assume the ATM machine's only going to spit out 20s. They have like fancy ones that can now, you can like say, I want 50s and 5s and, yeah. Yeah, I went to like a Chase Bank, and there was like, they replaced all the tellers with these machines. There was only like only if you're gonna buy like a home loan or something, like there was a dude to help you. Huh? Inside the bank. Inside the bank. Yeah. The robot revolution is happening, all right? Yeah. We're gonna have to defend ourselves with EMPs or something, I don't know. Okay. So we don't reject this, and this means we do not have evidence that the military is not 16% women. Yeah, I mean, they had a few employees inside the bank, but it was like maybe like two. I saw like two humans in the bank, and it was like a wall of these really fancy ATM machines that you could.
Wait, why do we decide that we don't have the evidence again? By the part.
Yeah, so this means, so I didn't write out all of the stuff, but basically it says, because the claim is that the military is 16% women, okay? What happened is we took a random sample and we only got 13.5% women, okay? And so the question is, could this result have happened from random chance alone? Or is it an indication that, that the military is something other than 16% women, okay? And it turns out that it could happen from random chance alone about 33% of the time, okay? It's like 1 in 3, right? So anytime you take a sample of 200 people from the military, it's quite possible that you get only 13.5% women, okay? And so because of that, we can't say that the military is something other than 16% women. Yeah.
So if the p-value is point like 0.337,
Yeah.
you could say the opposite, because then it'd be less than
Correct.
alpha.
Correct. So in this case, what the math is saying is that the reality that we observed, 13.5%, is not very different from the expectation of 16%. That's what it's saying, okay? In another scenario, right? So when we did the is our friend cheating, we had 30% versus 50% in both cases, right? One we played 10 games and one we played 1,000 games. In both cases we were saying, is 30% different from 50%? In one of those situations, the reality of 30% and the expectation of 50% was not very different. And in the other scenario, the reality of 30% versus 50%, the expectation of 50% was very, very, very different. That was the Powerball 4 weeks in a row scenario. That's very different. So what this is saying is that the reality versus the expectation, the reality of 13.5% versus the expectation of 16% is not very different because the p-value is quite large, 33%. Yeah.
If you were to write this in a textbook or something, you would write, in the U.S. military, we found that there's an estimated 16%. So the word estimated is the correct word.
No. Here, it's correct as it is written. We do not have evidence that the military is not 16% women, okay?
And saying 16 and 13 is not so different.
Yeah, we're saying, I guess another way you could write this is that 13.5% is not statistically significantly different from 16%. If you want me to write that, I can write that too, okay? Or, I mean, it's not significantly different from 16%. You can say that, right? I can write that. 13.5% women is not significantly different from 16% women in a sample of 200. Okay. All right, is that okay? All right. Okay, last section in chapter 8. All right, so this one, we are going to compare two samples and their proportions, okay? So here we are comparing two samples. Okay? And basically we want to know, do the samples provide evidence that the populations are different? Okay? So I mean, here's a, you know, let's say we surveyed people and we said, is your favorite color pink? All right? And we asked, and this is like gender stereotypes here, but let's say we asked 30 men this question, or let's say 50 men, and we asked 50 women, okay? Or I don't know, the samples need to be large enough so we have 10 successes and 10 failures, okay? So maybe we have to ask more. But, and then, so basically in our sample we get, you know, this percentage of men said pink is their favorite color, and in this, for the women, this percentage of women said pink is their favorite color, okay? And the question is, okay, if these, if the percentages are different, does that reflect that in the population, the proportions are different? Does that make sense? So we're just asking, based on what we see in our sample, can we then conclude that overall, a different proportion of men like the color pink versus women who like the color pink, or something like that, okay? Sorry, I chose a dumb example like that, but basically we're just asking, based on what we see in a sample, can we then conclude that what's in the population are different, okay? If sample 1 looks different from sample 2, does that mean the respective populations, are they different, okay? So comparing two samples, okay, so, you know, we observe sample 1 and sample 2. Okay, sample 1 has proportion p hat 1 of whatever, okay? Sample 2 has proportion p hat 2, okay? If p hat 1 and p hat 2 are different, does that mean population 1 and population 2 have different proportions? That's essentially, p hat 1 is different from p hat 2. Does that mean population 1 and population 2 also have different proportions? Okay. Does this scenario make sense? Yes.
Could you switch it either way in the same question?
What do you mean?
P hat 2 different P hat. Like, could you screw
Oh,
around
the
with
labels.
P1? Well, not the labels, but like when you're writing it out, you screw around with P2 and P1.
I like what I call sample 1 and what I call sample 2 is arbitrary. So if you want to call sample 1 men and sample 2 women, that's fine. If you want to call sample 1 women and sample 2 men, that's fine, okay? Or sample 1 is people who own dogs and sample 2 is people who don't own dogs, I don't know, whatever, okay? You can have 2 different samples and whatever. So, yes?
Define this mean value or net alpha. What does that mean?
Yeah, I think that's a topic for a later lecture of exactly what this 5% means and all of that. Okay, so right now it's just going to be this thing called the significance level, and it fits in this process, and we can talk about exactly what it means at another time. Okay, so this is what we're going to do. We're comparing 2 samples. So if we talk through step 1 of creating our hypotheses, there's one nice thing here, is that the null hypothesis is always going to be P1 is equal to P2. Basically, we're saying population 1 and population 2 have the same proportion. Okay? Okay, so here's, I don't know. I'm trying to think of a good example. Okay, and then the alternative, again, is identical to the null hypothesis, except the equal sign is replaced with something else. So this could be P1 is not equal to P2, or P1 is greater than P2, or P1 is less than P2. Okay? So this is going to be your alternative. There is an alternate writing of this, okay? So the null hypothesis could also be written as P1 minus P2 is equal to 0. So all we did is just, if we did algebra, I subtracted P2 from both sides, and I would get P1 minus P2 is equal to 0, right? Can you guys see that? So this is, these can all be written exactly the same way. So I could also have P1 minus P2 is not equal to 0, or is greater than 0, or is less than 0, okay? But your null hypothesis is always going to be either this or this, but which are exactly the same thing. Okay. Step 2 is the same as before. Check your conditions and use alpha equal to whatever. Okay. And use alpha. Okay. Or identify alpha. Okay. The process here, in comparing two samples and everything else, the process is exactly the same as it was before. All the changes, however, happen in step 3 when it comes to calculating your p-value. Okay, calculating the test statistic and getting your p-value, it's just this part has changed. Okay? Can I flip to the next slide? Okay, so as far as step 3 goes, this is for comparing two samples. Okay? So you're going to have to calculate your standard error, okay? So 3A, so I'm going to call, maybe there's a 3A part 1. Okay, so 3A part 1, you have to find our overall p hat, okay? So there's an overall p hat, okay? So if we look at our data is going to be, you got sample 1, which has N1 and X1, right? And sample 2 has N2 and X2. And then you can get P hat 1, which is X1 over N1, and then P hat 2, which is X2 over N2, right? We're just getting it's like the size of your sample and the number of successes, and then you get the proportion by doing X over N. That part's familiar, right? And we just have 2 of them because we've got 2 samples. That's good with everybody, right? Okay, so as far as step 3 goes, you have to find your overall p hat, which is going to be X1 plus X2 divided by N1 plus N2. Okay, so this is the overall kind of success proportion that you have. You add X1 and X2, and then you divide that by the quantity N1 plus N2. So this is going to give you your overall p hat. You have to do that first. Okay, and we just call this p hat. Okay. So when you have 2 samples, you've got p hat 1, you have p hat 2, and then you have an overall p hat. All right, and then so as far as calculating your standard error, this is standard error. It's just an ugly formula. There's nothing I can do about that, all right?
Is that the part 2 on 3?
Yeah, this is part 3A, I guess part 2, okay? Because 3A is calculating the standard error, right? Okay. So the standard error is just overall p hat times 1 minus the overall p hat times parentheses 1 over n1 plus 1 over n2 close parentheses. Okay, it's just, that's it. Okay, that's the standard error. That's it.
Wait, it's not over anything?
No, this is it.
This is the overall p-value.
This is the standard error. This-
Standard error is the same, deviation, right?
yeah, this is the standard error, the sampling distribution of the quantity p1 hat minus p2 hat, if you want to be technical.
But are you using the overall?
Yes, this p hat that appears here, this is the overall p hat. Okay, it's not, you don't know, you notice there's no p hat 1 or p hat 2 in here. It's this p hat. Okay, but you do use this n1 and you do use this n2. Okay.
What would be the given in the question?
So in the question you'll have n1 and n1, n2, x1, and x2 given, and maybe p hat 1 or p hat 2 given. Okay, I mean it's possible they give you n2 and p hat 2, and then you got to figure out x2 yourself. Okay, I don't know. Basically, for sample 1, 2 out of these 3 will be given, and you can figure out the other ones. Okay. Given 2, you can figure out the third. Okay, is that all right? This is your standard error, okay? All right, your test statistic, 3B. Test statistic. Okay, this is your observed minus the expected divided by the standard error, okay? So if the null hypothesis were true, the quantity we observe is p hat 1, and we would expect it to be equal to p hat 2. Or we could say the quantity we observe is this, and we're expecting this difference to be 0, okay? So either way you look at it, in the numerator we have this, okay? And then we divide this by the standard error, which is this ugly thing up here. Okay, so you get your test statistic. Okay, 3C, go from test statistic to p-value, and it's the exact same as before. Same as before. If the alternative has a greater than, you take the area to the right. If the alternative has a less than, you take the area to the left. If the alternative has a not equal to, you do 2 times the tail area. Okay, so that's same as before. And then lastly, step 4, this is also same as before. Make your conclusion. If the p-value is greater than alpha, do not reject the null. And if the p-value is less than alpha, reject the null. Is this okay? Yeah? All right, so we'll do an example and then we'll call that a night. Yeah, question?
So I guess this was my question from before. When you're doing your test statistic,
Yes.
how do you determine the order of P1 and P2? Is that given in the question that, like, you're given 2 samples?
Yeah, I understand. I understand what you're saying. Okay, so you have P1 minus P2 and it's arbitrary. Yeah, you could switch them around and you'll just get one will be the negative of the other. And then when you look it up, what happens is that if you switched them around, your alternative hypothesis, if it's a greater than in one way, if you switched them around, the alternative will switch to a less than. Okay? And then therefore, when you look up your p-value, it ends up being the same, because in one situation you're looking up, the area to the right of a positive z-score, okay, and in the other you'd be looking up the area to the left of a negative z. So you end up getting the same, okay? All right, so let's try out a problem here, okay? So I'm gonna just do a silly example, I don't know. do, I don't know.
Are there any new steps?
Huh?
Are there any new steps with the
No, it's the same 4 steps. Okay, the only thing that really changed is 3A and 3B. Okay, those are really the only things that have changed. Okay, everything else is pretty much the same. Okay, okay, so we'll say the question is: are there more truck owners in Texas than in California? Okay. I'm just playing to stereotypes here. Okay. All right. So we'll say we gathered data from random selection of Texans and Californians. Okay, so this is our data. Our data. Sample 1 will be Texas. And let's say we interviewed, I don't know, 200 people. And how many of them own trucks? Okay, we'll say 100. 100 own trucks, okay? Sample 2 will be California, and let's say we surveyed 300 people in California, okay? And it's fine that we have two different ends, okay? And X2, I don't know how many people in California own. Yeah, let's. I'm just say 90. Okay, I'm just making this up. All right, don't be mad at me. Okay, so what we get is so if we say, so this is what's given to us, and then we're gonna ask, do we have evidence that more people in Texas, or a greater proportion, a higher percentage of Texas owns trucks than California? Okay? All right, so the question is okay, so if we look at Texas, what's our proportion? What's our p-hat? 100 over 200, we have a proportion of 0.5. Okay, if we look at California, our p-hat 2 is 90 out of 300, we have 0.3. Okay, and the question is 0.3 significantly different from 0.5? That's what we want to know, okay? So we're getting 30% over in California, 50% in Texas. Does that mean if we looked at the entire state, we would get different proportions? That's what we're asking. Or could these results just be because of random sampling, that we happen to get 30% over here and we happen to get 50% over there? Could it also just be a result of random sampling? Okay. All right, well, let's go through the process. Okay, step 1. What is our hypotheses? So the null hypothesis is always going to be P1 is equal to P2. That's always, we don't even have to do any thinking. We can just say that's going to be our null hypothesis. And then the alternative is we're saying we're expecting what? Higher percent of Texas than California. So we're expecting P1, which is Texas, to be greater than P2. Okay?
Why do you expect that?
Huh? Because the question says, do we have evidence that a higher percentage of Texas owns trucks than California? Okay? So, all right, step 2, we're going to check conditions, and again, for the sake of time, we're going to say conditions met. Okay, I write these problems keeping in mind that I want the conditions to be met, all right? All right, and the conditions are met, and we're going to use alpha equal to 0.05. All right, so let's, we're going to take our data, and we'll make our, we'll do all of our step 3A, 3B, whatever nonsense. Not nonsense, excellent methods. All right, okay, so step 3A part 1, okay? We want to find our overall p hat, which is x1 plus x2 over n1 plus n2, okay? So let's take a look at what our data is, okay? So this is our data. So what is p hat? This is going to be, on the numerator we have 100 plus 90 divided by 200 plus 300. So our overall p hat is 190 over 500, and that's, I don't know what that is. Thank you very much. Okay. So our overall p hat is 0.38. Okay. Now we do that fun formula. Okay. So our standard error is equal to the square root of p hat times 1 minus p hat over 1 over n1 plus 1 over n2. When you teach this class over and over, it's like all of these things you just learn, okay? You'll be able to have a note card. I'm not going to expect you guys to have all of this memorized, all right? So you're going to have 0.38 times 1 minus 0.38 times 1 over 200 plus 1 over 300. Is that okay? All right, so I'm going to just punch that into my calculator. 0.38 times parentheses 1 minus 0.38 close parentheses times open parentheses 1 divided by 200 plus 1 divided by 300 close parentheses equals square root of that equals 0.0443. 0.004431, okay? So it's just a matter of getting this into your calculator and getting this, all right? So that's our standard error. Good? We're good? Okay. All right, and then we're going to get our test statistic. So this would be step 3B. So our test statistic is p hat 1 minus p hat 2 divided by our standard error, okay? So what is p hat 1? 0.5, right? You probably have this on in your notes that it's the proportion of Texas that owns cars, 0.5. Proportion of California that owns cars, 0.3. And we're going to divide by our standard error of 0.004431. Okay, so I'm going to put in 0.5 minus 0.3. And actually, because this is already in there, I'm going to just hit divide by the answer key on my calculator. Okay, so now I am 4.51 standard deviations away from the mean. This is my test statistic. Okay.
Proof that it's not right.
Okay, well, it's evidence. Yeah, we don't want to use the word proof. Okay, so at this point, so step 3C would be to go from the test statistic to a p-value. Okay, so we look up 4.51 to get a p-value. Okay, but if we go to our tables, 4.51 is off our charts, right? And we're trying to get the area to the right of positive 4.51, okay? Actually, in the little corner of your table, it has z is equal to 4.5, okay? So we can kind of approximate this because we have something pretty darn close to 4.5, right? So z equal to 4.5 gives an area equal to 0.99999. How many nines? 1, 2, 3, 4, 5, and then 6, 6. Okay. So that's the area to the left. Okay. And then So when we do, because our alternative, if we check out our alternative, the alternative has a greater than sign, right? So that means we want the area to the right. So the area to the right is 1 minus that, which is going to be, 1 minus 0.12345 0.000034, okay?
Evidence.
Yes, so this is my p-value. Is that okay?
Where did we get zeros?
I did 1 minus 0.9999966, okay? Which was, if I looked up z equal to 4.5 in the table. Okay, so my p-value is very, very small. And so the conclusion is my p-value is less than alpha, okay? So we say we reject the null hypothesis.
Step 4, right?
Yeah, this is step 4. Making our conclusion, okay? And we say we have evidence that the proportion of truck owners in Texas is higher than California. Okay. Okay, I know this is a lot to take in one day. I promise you, you do practice and you'll get better at it, okay? It feels overwhelming. Anything you see for the first time in your life feels very overwhelming, okay? But with practice, you'll get better at it. Okay, we'll see you guys next week.